Welcome viewers. In this video, we will discuss Taylor series expansion of function of z. At first, I will mention two important results related to complex variable. The first one is known as Cos Integral Formula, which is given by the relation f of z0 1 by 2 pi I integration over closed loop function of xi d xi minus z0, where xi is a complex variable and z0 at some point where the function is being evaluated by this integration. The second important result which I want to mention is the nth derivative of the given analytic complex function, that is given by this relation n factorial 2 pi I integration f of xi d xi minus z0 to the power n plus 1. To find Taylor series expansion, we will start from Cos integral formula, which is given by this relation. The first step is to write Cos integral formula f of z 1 by 2 pi f of xi d xi minus z. Here we have considered a complex plane given by two axes, the real axis x and the imaginary axis iy. Here we have considered some complex region given by gamma, in which we consider a circular contour given by c, and the center of the circle is given by the point z0. Here z is some arbitrary point and xi is the point on the contour. So we can denote the position from the origin by this arrow, or you can say position vectors, and these are from z0 to z is z minus z0, from z0 to xi is xi minus z0, and from xi to z is z minus xi. Here function of z obviously analytic in this region circle C, and we want to expand the function of z in this region gamma within the circle at center at z0. Therefore we considered at first the Cauchy's formula, integral formula. Here z minus z0 is less than capital R, where R is the radius of convergence, where R is radius of convergence. At first we will develop a series expansion for this factor 1 upon xi minus z. For convenience, we will set kt as z minus z0 xi minus z0. To find the expansion for this factor, we considered this term kt defined by this relation. Now let us subtract unity from both sides. 1 minus kt 1 minus z minus z0 by xi minus z0. This results in xi minus z divided by xi minus z0. We can invert both sides and we will get 1 by 1 minus kt given by xi minus z0 xi minus z. So what we are getting? We are getting this factor which we want from this relation. We get 1 by xi minus z equal to we can get 1 minus kt to the power minus 1. So we are writing this by this term, and this term will be 1 upon xi minus z0. Now if kt is less than 1, we can write 1 by xi minus z0 summation n equal to 0 to the power infinity kt to the power n. This can be expanded by this series for if we consider this condition. So finally we can substitute the value of kt here and we can get the expansion of 1 by xi minus z by this relation 1 by xi minus z 1 by xi minus z0. We get in the previous page, I am writing the result again, that is kt to the power n. Now I will substitute the value of k2 xi minus z0 n 0 to infinity summation z minus z0 xi minus z0. This is kt to the power n, and ultimately 1 by xi minus z is given by this expansion series z minus z0 to the power n divided by xi minus z0 to the power n plus 1. Now we will come back to the DeCasas formula, which is given by 1 by 2 pi I f of xi d xi minus z. This is nothing but the DeCasas formula is equal to this factor 1 by xi minus z. I will substitute here and will find this is given by 0 to infinity 1 by 2 pi f of xi and d xi, and now we'll substitute this factor 1 by xi minus z by this expression and to the power n divided by xi minus z0 to the power n plus 1. Now we will use the result of nth derivative of fz, which is, you can see, that is a term n factorial and also xi minus z0 to the power n plus 1. So this term, this integrand, can be substituted by the nth derivative of function of z. So we will do this. Here we will use the nth derivative, the formula for the nth derivative of function of z, and we will get the result as 1 by 2 pi I f of xi d xi minus z0 to the power n plus 1. So this whole factor is nothing but the nth derivative of function of z. Along this, with this I have z minus z0 to the power n, and with, of course, the summation n equal to 0 to infinity. So I separate this term here and write the rest of the part with the integration. This is, so the bracketed term will be reduced to the nth derivative of function of z, and this can be written as n equal to 0 to n infinity, and it is nothing but fn z0 z minus z0 to the power n divided by a term will be there factorial n from this definition, factorial n. So we substitute this integrand by this nth derivative of function of z0. Ultimately, we see that this factor, which is given by Cos's formula, this is actually nothing but function of z, and we derive this term as by this series expansion that is given by here. So we can expand this term by term, and we will get function of z0 and first derivative z minus z0 and so on. So this is nothing but the Taylor series expansion for function of z at point z equal to z0. If z0 equal to 0, then this Taylor expansion becomes the Maclaurin series for analytic function, complex function, function of z. So that's all. This is a simple derivation for Taylor series expansion and Maclaurin series expansion for complex function. Hope you like this video. Please like and share, and also don't forget to subscribe my channel. Thank you.